Second section in Trig, labeled 1.2, is about angles. So first we're going to go over a little bit of vocabulary. So first, this is supposed to say line, got a little worn away. A line is something that passes through two distinct points and continues in two directions without end. So it's important to distinguish a line versus a line segment. So a segment would have two endpoints, and it would contain all the points in between those two endpoints. A ray has one endpoint and then continues forever in the other direction. And you have to be careful when you name your ray because you have to begin with the endpoint and end with the other point on the ray. An angle is formed by two rays and have a common endpoint called a vertex. So I'll review from geometry class. First of all, positive angles, we talked about this in the last lesson, but we measure them in a counterclockwise direction. So positive angles will go like this, open from this side over. And this positive x-axis we call the initial side, and that's where we measure everything from in a trig unit. Negative angles would go in a clockwise direction, so they would measure like this. Again, starting from the positive x-axis and measuring in the clockwise direction. Degrees are the most common measurement for our measuring of angles. We're going to learn something else called radians, and on your ACT they like to use radians quite a bit. I'm not really sure why, they just do. So, types of angles: acute between 0 and 90. They must be less than 90. So a right angle measures exactly 90, an obtuse angle measures more than 90 but less than 180. And a straight angle is exactly 180 degrees. We talked about these in the last lesson as well. Complementary angles add up to 90, supplementary angles add up to 180. So if I look at this picture, 6K and 4K, I see that they form a straight angle, which is 180 degrees, so they must be supplementary. So if I was to add these two together, I would get 10K equals 180. And then K is 18. Now we can't stop there because I think they actually wanted the measurement of the angles. So I'm going to go back to my picture. If I plug in an 18, I get this to be 108 degrees, and I get this to be 72 degrees. You don't want to solve these through guess and check because we're going to do some algebraic ones soon, and it would just be a very bad idea. So find the angles. 6M and 3M are complementary this time. So 9M has to add up to 90 degrees. Therefore, M is 10. And again, go back and find the actual angles. If M is 10, this is 60, and this is 30. So I'll review so far. Right triangle trig, you might remember from Algebra 2, or geometry. Sine, cosine, and tangent were some trig functions that we looked at. So first, I want to remind you what these measurements meant. The sine of an angle is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. Now the words opposite and adjacent are in reference to whatever angle we're referring. So the first example, they want you to start at angle A. So I always tell my kids to draw a little smiley face here and think of themselves as standing at A. So the sine is opposite over hypotenuse, so the opposite of A is little a, hypotenuse is C. The cosine of A would be adjacent over hypotenuse, so B over C, and the tangent would be opposite over adjacent. Now we're going to totally change it up, and this time we're going to stand at B. So sine of B would be opposite over hypotenuse, so B over C. The cosine of B would be adjacent over hypotenuse, which is A over C. And the tangent of B is opposite over adjacent, so for him it's B over A. And you should notice some similarities. The cosine and sine just end up switching when you switch angles, but the tangents are going to be reciprocals of one another. So let's look at the coordinate plane. This is the rectangular coordinate system, and our x-axis is here, the horizontal axis. This is the y-axis. Whoops. This is the y-axis. And the quadrants are 1, 2, 3, and 4. This is quadrant 1, and then it goes in a counterclockwise direction. This is quadrant 2, quadrant 3, and quadrant 4. That's a Roman numeral 4. So just to refresh your memory, when we're plotting points, the first part of the coordinate is the x, and the second part is the y. So the point 1, 5 is over 1 and up 5. Sometimes children get confused with slope and plotting points because they're totally opposite. B is negative 2, 4, so left 2, and then up 4. You should label your points with the letters. C is -3, -2. D is 3, 0, so right 3 and then up nothing. And E is 0, -2, so up, right or left nothing, but down 2. Any point on the x-axis, so for instance D was on the x-axis, is going to have the generic form, we're going to call it x, 0, indicating that the x can be anything, but the y value must be 0 if he's on the x-axis. Now conversely, on the y-axis, just like point E, the x value must be 0, but the y value can be anything. So if we're graphing the line 2x minus 3y equals 6, you had two methods, and depending on how lazy you are, you're going to get the answer really fast. For me, this is standard form. I always like to think about finding the x and the y intercepts and then just connecting them. So since I know the x-intercept will have a y value of 0 and the y-intercept will have an x value of 0, I just think about plugging in zeros for those. So first, if I plug in a 0 for the y value, I think about covering up the y, and I get 2x equals 6. So that means x must be a 3. And for the y-intercept, if I plug in a 0 for the x, I end up with -3y equals 6. So y must be a -2. And now I can quickly graph these. 3 zeros right here. And then 0, -2 is right here. And then, ooh, pretend that's a straight line. It's a little hard to graph on the tablet. That's what my line looks like. You could have also solved for y. So, if you got y by itself, first you probably would have subtracted the 2x over. And then you would have divided everybody by a -3. And you would have ended up with this line 2/3 x minus 2. So you would have started at -2, and then your slope was up 2, right 3. So you would have ended up plotting the exact same points. It's just up to you which method you'd like to choose. As you become a little more developed in your math skill, most people find that x and y intercepts are a little quicker when you're in standard form. Now when you have a parabola, sometimes it's given to you in this form, and this is called vertex form. Whoops. V, not y. Vertex form is just one form of a parabola that we saw in Algebra 2, but we saw it quite a bit, and we're going to see it again here in Trig. The vertex is at the point HK. If A is positive, then the parabola opened up, and if A was negative, the parabola opened down. If the A was less than 1, so like a 1/2 or a 1/3, that meant the graph was fat or flat. Than the original y equals x squared, and that's because it's going up maybe half as fast as it used to go up, so that's why it becomes a little fatter. If the a is greater than 1, the absolute value of a is greater than 1, then that meant the graph was a little skinnier, so it was going up 3 times as fast or 4 times as fast. Let me move this out of the way. So let's go ahead and graph y equals x minus 4 squared minus 2. So first I see that my vertex is at 4, -2, so right 4 down 2. And then I would always have my children pull some points off of a calculator, or you can just do them in your head even. If I go 1 to the right, that would be a 5. So think about plugging in a 5. 5 minus 4 is 1. 1 squared is 1. 1 minus 2 is a -1. So I'm going to plot the point 5, -1, and then they always have symmetrical points on parabolas. So I'm not looking for beautiful art here today. My vertex here in the next example is at -4, 2. So I plot -4, 2. And then again, I need to plot something to the left, something to the right. So I'm going to start with the point x equals -3. If I plug in a -3, I end up with 1 squared, which is 1. 3 times 1 is 3. 3 plus 2 is 5. And you're going to notice that this is a much thinner parabola. And that's because the a value was a 3, which makes it go up 3 times as fast. The equation of a circle that's at the origin is in this form, in the coordinate plane. So the center is at 0, 0, but the radius is some other value. So when I look at this example, my center is at 0, 0 still, but if this equals my radius squared, that must mean my radius is a 4. So I graph my center of my circle at 0, and then radius of 4 means I'm going to go 4 in each of the up, down, right, and left directions. And then since I have a terrible time graphing a circle, oh jeez. Pretend that's a circle. Oh, that's really bad. This is supposed to be a circle. Make sure yours looks a lot better than mine. Alright, moving along. If we weren't sure what that graph looked like, we could do this on our calculator. Now, I'm not going to show you on my calculator, but if you took this equation and you solve for y, so first thing I would do is I would subtract the x squared over, so it would be 9 minus x squared, and then you would have to square root both sides. And then remember, in algebra, when you square root something, it's both the positive and negative value of whatever you square rooted. So on my calculator in y1, I would type the square root of 9 minus x squared, and in y2, I would graph the square root of back up. I would graph the negative square root of 9 minus x squared. So this is going on my calculator. And in the standard window, you would see that it would graph one arc and then another arc, and it would graph a circle for you. The distance formula, you need to know it. There are no excuses at this point in your life. You must know it and know you can't use programs. So x2 minus x1 squared, whoops, plus y2 minus y1 squared. So find the distance between these 2 points. Now I kind of cheat, and instead of using the full-blown formula, I just think about distance itself. So between 2 and negative 1, that's 3 units. It doesn't matter if I put 3 or positive 3 or negative 3, because I'm going to square it in a minute. And 1 to 5 is 4 units. And again, it doesn't matter if I put positive or negative, because I'm going to square it. So this ends up being the square root of 25, which is the answer 5. Then, let's see, where are we at? Find the distance from the origin to point xy. So the origin would be the point 0, 0, and then any generic point xy looks like that. So if I'm doing distance formula, the distance between 0 and x is just going to be x units. So I'm going to call that x and then square it. Same thing with the y's. And since I don't actually have numbers, I can't solve. So this is the generic formula for the distance from any point to the origin. Okay, angles in standard position. It is in standard position if the initial side is along the positive x-axis, which we discussed was right here, the positive x-axis, and the vertex is at the origin. So it can open up in either direction, but generally if we want it positive, we want it to open up in the counterclockwise direction. So if we want to draw a 45-degree angle, 45 would be half of 90, so just kind of eyeball it, it looks like this. That's what a 45-degree angle looks like. Now the question is, find a point on the terminal side. So I'm going to just say this is my point, and I don't really know what he is. So I need you to think about this. What if I were to drop a line straight down? I know that this is a 45-degree angle, and I know that this is a 90-degree angle, which means this is also a 45-degree angle. So it looks to me like we have a 45, 45, 90 triangle. So I want you to think about your pattern for 45, 45, 90s. I know that the sides on the bottom and on the legs, the bottom and the vertical, are going to be the same value. So for instance, if I went over 1 unit, I have to go up 1 unit for this to be a 45, 45, 90 triangle. So the point 1, 1 would work. If I went over 2, I'd have to go up 2 for this to be a 45, 45, 90 triangle, and so on and so on. So any point that's on the terminal side of a 45-degree angle has to be in the form, and I'm just going to generalize it, A, comma, A. And that A could be anything that is, in this case, positive. Alright, moving along. Draw an angle of 135 degrees this time. So, if we think about starting on the positive x-axis right here, and then opening in the counterclockwise direction, 90 is not far enough, 180 is too far, so I got to figure out how far do I need to go. Well, 135 is 45 degrees beyond 90, so kind of right there. And we open up in this direction, and that's 135 degrees. And this time I need to find a point on the terminal side of that angle. So any old point will do. So the question is, what does that point look like? So once again, I'm going to drop a line down from this point. And I want to think about angles. And I want you to look at this triangle right here. If this is 135 degrees, that means right down here, this has to be a 45-degree angle. So I think, again, we've got a 45, 45, 90 triangle, which means that the horizontal and the vertical legs have to be the same distance. So as an example, this is just an example, if I went left 3 units, because this is left negative, I'd have to go up 3 units. So that would be one example of a point on the terminal side of that ray. It could be negative 4, 4. It could be negative 1, 1. So to generalize our point, it would have to be negative a, comma, a for any positive a value. Alright, the next line says if angle theta is in standard position and the terminal side lies in quadrant 1, then we say theta lies in quadrant 1 and we abbreviate it like this. Theta is contained within quadrant 1. If it says this, that means it is in quadrant, Roman numeral 2. And then theta contains in quadrant 3 would look like this. So they use Roman numerals to determine which quadrant we're talking about. So quadrantal angles have terminal sides that are along one of the axes. So an angle that is quadrantal could be, let's see, this angle right here. From here to here would be a 90-degree angle. There's a whole bunch of them. There's 90, and then the next one would be if it went all the way to the next axis, so 180. We can go down to 270, and then back up all full one rotation would be 360. There's also negative quadrantal angles. There's all sorts of them that we could list. Coterminal angles, that's our next concept. Coterminal angles are 2 angles in standard position that have the same terminal side. So for instance, it's just 2 ways to name the same angle. A 60-degree angle would be positive measurement, so it would start here and measure up 60 degrees. That would be 60. But if I decided to measure in the negative direction and go all the way around to the terminal side this way, I would have to go 300 degrees to get there. But they happen to be the same terminal side. So those are called coterminal angles. And the easiest way to find them is just to either add or subtract groups of 360. There's many, many answers for coterminal angles. So if 60 is the angle I'm talking about and I want to find another coterminal angle, instead of subtracting 360, how about this time we add 360? And we're going to get 420 degrees. That is one example of another positive coterminal angle for 60. If I look at the angle of 40 degrees, they want me to find a positive and a negative coterminal angle. So let's start with the negative. Instead of adding 360, if I want my answer to be negative, I'm going to have to subtract 360, and that's going to give me negative 320 degrees. And then if I start with 40 again, if I just go ahead and add one 360 group, that's going to bring me up to 400 degrees. There are many, many, many answers to that question. That's just one example for each, the positive and the negative coterminal angles for 40 degrees. You could keep adding groups at 360 or keep subtracting groups at 360. So when I ask you this on your homework, there's more than one right answer. And that completes our lesson on 1.2. Go ahead and look for your 1.2 book assignment. I'm sure it's a lengthy one.